All right. Hello, everyone. This is Silviu Livescu from University of Texas at Austin, and I'm also the technical director of the Society of Petroleum Engineers for Data Science and Engineering Analytics. And so today I welcome you to our session about the SP Datathon we have been organizing in the last 2 months for Pivot, and so I'm more than happy to share with you the outstanding work that our participants have done, and I also want to thank all the committee members, judges, all our partners who help us make this Datathon such a wonderful experience. So before I start describing the problem statement, I would like to say that the Society of Petroleum Engineers, for those of you who don't know, is the largest professional society for the oil and gas professionals. And so we have close to 140,000 members right now. And so a lot of things are going on, and I'm more than happy to bring together the oil and gas professionals with the geothermal professionals and the data scientists and everybody else. So this Datathon has been built on 2 other Datathons that we organized last year. One of them was organized in North America by the 2 largest SPE sections in Houston and Calgary. And the other one was organized in Europe by 4 sections, outstanding team effort between London, the Netherlands section, the Italian section, and the Romanian section. And so this year, we brought together the Forge team, the US Department of Energy team, to use the data, and we are going to talk a little bit more about that. But so for those of you who don't know, Forge, and I'm putting here a link, is the Frontier Observatory for Research in Geothermal Energy. It's a great research project in Utah happening right now. And so again, for those of you who don't know what Forge is about, I'm encouraging you to go to their website and find a plethora of information about what's going on. In addition, there is the Geothermal Data Repository, a 10-year-old project, sponsored by the US Department of Energy. And here's the link for that. They have more than 200 gigabytes of geothermal data, a lot of data there, a heaven for data scientists. And so we use that for this Datathon. Our scope was actually to use the data for an injection well that just was stimulated at Forge in June, and use that data to run different, data science magic to determine the theoretical optimal producer placement for an enhanced geothermal system, with the output of a maximum power generation over 20 years. And so, as I said, it's a lot of data available on the GDR website, and Andy Adams from the Geothermal Technologies Office at DOE put these matrix together, a lot of data everywhere. And then Luke Frash, who is on our panel today, came up with this kind of very simplistic information about the data analysis approaches. So long story short, what we wanted was to provide the data to the participants, but we didn't constrain them to use any kind of algorithms. Everything was, we wanted them to use open source, software and approaches. We didn't want actually them to follow any kind of rules in their data analysis. And that was done on purpose because we want actually to enrich the creativity and the team building of the participants. But long story short, like we all know, for any enhanced geothermal system, it's a very complex problem, right? So in terms of what parameters we can play with, there's a lot of room, but as we all know, any analysis is very complicated because no one single parameter can have a very unique behavior, and we are going to see that. We got close to 100 participants, which for us was absolutely outstanding given the short time we had to organize this event, and we are going to talk a little bit more about that. And then we got 6 videos that we could use for today competition. And so these are the teams who sent us the videos. Again, we are absolutely pleased about the team effort, and we are grateful for all the participants' time and effort and enthusiasm. And so today, we are going to run a very short 12 minutes video of the 3 most effective teams for all of you to see. And so after the pivot, all 6 videos are going to be available for everybody to see them on the Project Inner Space website and also on the SP website. So for now, let's watch the 12 minutes video of the 3 most effective teams. The video, please.
I'm Ben Cassidy from Hammer & Tongs Polymer Development. I'm a chemist, and I entered the Pivot 2022 Datathon to learn more about geothermal energy and data science. So you can see here on the bottom left, we have this large red region of low enthalpy of production and 0 power output. So that means if you have low enthalpy of production below about 800 according to this, you're very likely not to get any power output whatsoever. Whereas you can see if you get enthalpy of production above 800, you have a much higher likelihood of actually producing some. So if you want to maximize the enthalpy of production, H-Pro, this requires sort of a careful balance between our input variables. So first we want to look at well spacing, how far the production well is from the injection well. And you can see as you increase well spacing here on the y-axis, go from 0 to 200 to 400, the density, the population density of H-Pro also increases. You can see the higher you go, the more likely you are to get a successful well, or well that has high H-Pro. Similarly, we want to keep the circulation flow rate, Q, we want to keep that low. You can see here, if we increase it past about 0.02, we really start to drop off in the number of wells that have an H-Pro above 800. However, H-Pro is not the only thing that we want to maximize. We also want to optimize the M-Pro, the production mass flow rate. And by convention in this data set, it's negative, so we're going to make this more negative. And the ways we can do this are by increasing the number of well intervals or injection intervals, and also by increasing the circulation flow rate Q. So you can see this is going to be sort of at odds. We want to increase Q in order to improve M-Pro, but we want to decrease Q in order to improve H-Pro. One last thing we want to take into consideration is that we can't make the well spacing too far. If we do that, then our fracs won't intersect the production well. And of course, like I already said, if our spacing is too close, our injected water won't heat up. We won't get a high enough H-Pro. So the best idea is to increase the spacing, then tailor the Q to hit that sweet spot. And this is going to be pretty important going forward. You can see here on this plot, we have P out on the x-axis, and that's a log scale, and we have Q on the y-axis. And you can see there's a spot right there in orange that has a relatively, it's relatively easy to hit, but it has a very high P out compared to most other populations on this table. Step 1, we're going to optimize that sweet spot using the 30-year data set. So first we take a slice containing all data that has well intervals equal to 6, and then we take a slice centered around a well spacing of 700 meters. Then we see that in order to hit that sweet spot, we need a Q of about 0.012 cubic meters per second. So that captures a large population with very high power production, and it doesn't capture any of these other problematic populations, such as large populations with zero power output, or this large red swath that has mediocre power output below at lower Qs. And taking a histogram of this slice, we can see that our median power output is 426 kilowatts. That's there in the bottom left. So this method minimizes probability of a failed well, and it has a low standard deviation in the expected power production. Other strategies either greatly increase the risk of a failed well, lowering the median power production, or fail to capture the region containing that maximum power production. And using this model replicates well on the other data sets provided. Doing the exact same thing, we hit the sweet spot on the 30-year more wells, 20-year wide, and the 1-year data set. The 20-year standard data set was not included because it had a low N once we got to this point. The next step is to add in the skew and phase variables, and this was done using all 20 and 30-year data sets combined. I found that we need to set skew to 0.075 and phase to 1.57, so vertically below the injection well. So before doing this, the median power output is 418 kilowatts, and after performing these final optimizations, we increased it to 544 kilowatts with a standard deviation of 225. So that's enough to power 440 US households, and it's comparable to a 1.5 megawatt wind turbine. So just to show you how far we've come, this is that same plot from the beginning of the presentation showing power output on the x-axis versus enthalpy on the y-axis. And you can see that after applying this decision tree that we formed, we're selecting for a population of wells on the very forefront of power output. So just to wrap things up, where should we put the production well? We should put it 700 meters away from the injection well, with 6 injection intervals, a Q of 0.012 meters cubed per second, a skew of 0.075, and a phase vertically below the injection well.
Hello everyone, this is Team Pebbles, and we're excited to share our work with all of you. Our workflow was the following. A good amount of time was spent on understanding the data. Then we applied data engineering, like creating the necessary target columns. Then we used feature engineering in order to select important features. And lastly, we built a number of machine learning models. Our work is mainly focused on the data coming from the medium 20-year CSV file. So the next step was to deal with this imbalance by applying a number of treatments. So mainly we use 2, which is undersampling and oversampling. Each treatment scenario has its own advantages and disadvantages, while the first increased the true positive values and drastically decreased the true negatives. The second treatment actually did quite the opposite. And since the accuracy is not the best scoring method in classification problems, we use confusion matrices and RUC AUC scores to measure the performance of the models. We applied a regression. So random forest regression model had the best performance out of the 3 implemented models, AutoBoost, RF, and XGBoost. As we can see, the results for random forest are outlined here for P-usable net target and P-out net target. For classification undersampling, logistic regression did slightly better than the decision tree classifier, and here are the scores for logistic regression. Whereas oversampling, both logistic regression and decision tree had nearly identical performance as shown down here, which actually very close to the values we got in the second case. So meaning that we made an attempt in visualizing the 3D geometry data. And here we have a table illustrating the parameters of the placement of this well. For instance, we see that the spacing is 703 meters, whereas the length is over 1100, and that was for P-out net as a target column. But in conclusion, we built multiple ML models illustrating a reasonable performance of predicting P-usable net and P-out net. given the challenge and uncertainty behind transforming the time series data into a suitable format for our analysis. The introduced models do lay the foundation for the optimization of the production well placement, which by itself is a puzzling task. And of course, stronger technical knowledge and nuances of enhanced geothermal systems is necessary for tackling the problem of the Datathon.
Hello everyone, my name is Sarah and I'm part of Team Naturals from Stanford University. I'm here with my colleagues Jobs and also Lutfan, and we are going to present you our results on optimizing the well placement for Utah Forge production well. In this competition, our task is to optimize the production well placement against the 16A32 injector well. And we need to deliver a maximum power output over the 20-year lifespan while accounting for parasitic losses. This objective can be translated into objective function, and we took the liberty of expanding the objective function that was given in the kickoff into this formula. So first of all, we lengthened the period into 30 years, so we have a safety net for the power generation. We also add more loss terms for the power output calculation so that it can become more accurate. So for instance, we have power cycle loss, injection thermal loss, and also injection hydraulic loss for the power output as an objective function. Our team approached the problem by understanding that different geothermal operators might have different appetite to risk versus reward. And therefore, while presenting our recommendation for the most optimum well parameters and well placement parameters, we have to be able to quantify the risk aversion of the decision maker. And to quantify that, we present you this utility function right here, in which the R is the risk aversion factor. This is the result of our optimization, which is the well placement risk versus reward. And we captured the result in terms of the efficiency curve, which has the mean of the power output as the y-axis in gigawatts hour equivalent cumulative. And then the x-axis is the standard deviation, and then the points are colored by the risk aversion factor. So if you're up here, meaning that you have a low risk aversion factor, you're higher tolerance to risk and you like high risk with high reward. And for that, you'll get over 2,000 of power output, but with much higher standard deviation. And in order to achieve that, here are your most optimum well parameters as well as the most optimum injection parameters. Similarly, if you have high risk aversion, meaning you have lower tolerance to risk, then you can get a lower number of power output, but with much less standard deviation. So it is more precise. And you can see here that the parameter distribution is quite varying across the risk factors. So it is very important to the geothermal operators and decision makers to understand their risk profile and choose accordingly. In conclusion, we have demonstrated to you how we can quantify the risk aversion into utility function so that geothermal operator can decide on the most optimum well parameter based on their risk tolerance. And the optimum well parameters are generally consistent with what has been found and published around GeoDT high performance scenarios. And we also found that adding one or two more wells to the producer-injector pair can greatly increase the power output. However, the cost will also increase. Thank you very much for your time and have a good day.
All right, we are back. I hope you enjoyed the videos as much as we did. And with this, I would like to introduce my panelists, and I want to talk a little bit, for the next 20 minutes or so about the most effective teams, about the Datathon itself, and then we are going to announce the winners. And so it is my pleasure now to introduce the four panelists. Let's start with Professor Birol Dindoruk. So each one of you, if you can introduce yourself for 1 minute, it would be great.
Okay. Thank you very much, Silviu. Thank you very much, everybody. I am currently a professor of petroleum engineering and chemical engineering at University of Houston. And previously, I worked for Shell for 23 years. I was chief scientist of reservoir physics and principal expert of reservoir fluids. And I have also been a adjunct faculty for the same university for more than 2 decades. Thank you very much.
Welcome, Birol. Pushpesh?
Okay, thank you, Silviu. Hello, everybody. I'm Pushpesh Sharma. I'm the senior product manager at Aspentech. I'm responsible for HYSYS product suite. And as a background, I did my PhD in chemical engineering. My research was focused on enhanced oil recovery, but geothermal has been a passion of mine. So I was continuously working on that. And I was very fortunate enough to be part of all the datathons that Silviu mentioned in the beginning. So it's been quite a learning curve, and I'm looking forward to discuss about this datathon. Thank you.
Thank you, Pushpesh. James?
Hello, everyone. Yeah, thank you, Silvio. My name is James Ng. I'm currently a senior research scientist at a company called Pason Systems in the upstream oil and gas industry. Current research activities include drilling automation and some use of the data for drilling performance, and also a volunteer for the SB Calgary section. So this is actually my third datathon, and just want to congratulate all the participants for all their hard work. We're continually blown away by the quality of the work that's done, and everyone should be proud exiting this competition.
Excellent. Thank you very much, James. And Luke, I know, unfortunately, you don't have video, but if you can introduce yourself.
Yes, this is Luke Frash. I am a staff scientist at Los Alamos National Laboratory in New Mexico, and I'm a Colorado School of Mines alum. I got my start in geothermal research with my PhD project back at Colorado School of Mines, and I'm primarily a laboratory geomechanicist, and I do modeling as a hobby. And in this case, I was responsible for providing the synthetic simulation data for this datathon using a model that I developed. We used it to generate 100,000 different scenarios for geothermal designs at the Forge site, accumulating with about 10 gigabytes of data with timeframes that ranged from 1 year on the fast side to up to 30 years for the longer simulations. And in this competition, the competitors got to choose how they wanted to use the data that we provided, including the data from GDR from the Forge team itself.
Very good, very good. Thank you very much, Luke. So in addition to us 5 here, there are probably another 20 or so, committee members, SP members, judges. So in the last 2 months, we worked really, really hard for this datathon to happen, and we are so happy that we could present today the results. The first question I have for the panel, So we've been involved with other geothermal datathons. So let's talk a little bit, very briefly about how this one is different than the previous ones. I mentioned the 2 ones that we organized last year. How this is different? Pushpesh, can you start?
Oh, yeah, definitely. So, Silviu, I think this datathon, there are some aspect about the logistics of the datathon. So it was organized in a faster manner. But one thing that kind of pointed out to me, or I kind of realized during the organization, that the other datathon that we have organized, they were very open-ended, and they were a little bit simplistic in nature. So if you think about it, it's more, we were drawing the attention in, it's more about telling everybody what geothermal is about. And this datathon is more minutiae, it's more subject matter expert, it's more detailed. So, which is a very good, I think, graduation for geothermal technology. So we brought people in, and now we are seeing people apply the same concept in a more complicated way. So I felt like this is the trend, and this is a big difference. I feel like that we kind of graduated along the time.
Thank you, Pushpesh. And just for everybody to know, you are a member of the SP Gulf Coast section in Houston, which is the largest North American SP section. James, you come from SP Calgary section. So what's your perspective about the previous datathons versus this one?
Yeah, just to echo Pushpesh's comments, I felt this year was kind of a much more challenging problem, and once again, we're all blown away by the results. And I think what that says about the participants is that they kind of continually rise to the occasion, and if we keep raising the bar, I think the outputs of this datathon are getting closer and closer to kind of solving the actual problems. In fact, this particular datathon, the problem statement was much closer to what someone working in the geothermal space would try to do in kind of their job. So again, kudos to them. Another kind of difference between past datathons is that we've typically run boot camps and workshops before. And what those were geared towards was kind of providing kind of some basic digital skills training, as well as introduction to the kind of theme of the datathon. This year we didn't do that, so participants had to basically learn and apply on the fly, which again increased the difficulty of it. So those are kind of the two main ones that I saw.
Excellent. And just for everybody to know, you can Google actually the preview datathons organized by SPE, and you can still find on YouTube, on the SPE websites of the two sections. You can find the videos, you can find the bootcamp recordings and other details. So for all of you who want to start learning about data science and how it can be applied to geothermal energy, by all means, you can Google, or you can even contact us, and we are more than happy to provide links to those videos. Now let's move on. Birol, you saw the videos, so now we presented the three most effective teams. What do you think? How they did, and what do you think can be done better or differently if they had more time?
Yeah, I think I'm going to add it to my colleagues already mentioned how complex the problem is and how fast-paced it was. What I noticed is the diversity of approaches, actually, which amazed me. Some of the participants, they try to tackle problem themselves. Maybe they got help or not, but at least we go with the face value of what is submitted. But some of them were extremely diverse, actually. What I noticed is that the complexity level and knowledge level differed, and as a result, they went into shopping, so to speak, and they get other people around them so that they can tackle the problems. And also, I noticed that maybe this is the perception that I have, how they performed under pressure, because they have other things to do, obviously, all these participants here, and also how some of them exploited or took the advantage of the open-endedness, being open-ended, actually, because they went extra miles in some of them. Like in two of the cases I looked at it, wow, it's amazing. They even look at those details, actually. So I really liked it.
Excellent. Excellent. Look, what do you think about the six teams who sent videos, or about the three most effective teams? What's your perspective about what you see?
So there, in this competition, my favorite submission, perhaps, although we'll see, is maybe from Stanford, where they applied an additional layer of analysis to the problem, where they were actually looking not just at trying to find an optimization, but also looking at the risk factor associated with different options for what the optimum parameters might be for where to place the production well. So I found that quite a good approach. And then I also really liked the GOT team, or GOT 360, just because they had a great presentation. It was really fun to watch, and they really dug deep into how they tackled the problem, all the way down to what chocolates they chose to eat. So it was a pretty fun competition, and I agree with the idea that there is some nice, advantage taken of the open-endedness of the problem that we provided.
Right. That's absolutely right. I think from my perspective, having 6 different videos and none of them actually, no team chose the same path, from the problem solving all the way to presenting it. I think that's truly amazing, right? And then please, we need to mention that we did have one team that was a one-man show, actually. So that was also quite impressive, right? So we left it open-ended from the number of team members, right? From 1 to as many as they wanted. And so I think the most numerous team was probably 7 members, if I remember correctly. And so Pushpesh, what's your perspective about the most effective teams, the 3 most effective teams, the Pebbles team, for instance? Anything you can say about them?
Oh yeah, definitely. I think all the 3 teams have very unique perspective, and as Dr. Dindoruk mentioned, that it's the diversity of solution and the individual and everything comes together in the solution. For the Pebbles part, I really like that they spent a lot of time in exploratory data analysis, and they actually did a lot of work in understanding different variables. Some of the teams directly jumped into the modeling part and looked at the data with filtering, but they, I think, spent a lot of time on understanding how different parameters are interacting with each other. And I also like the way they used visuals. Some of the analysis was presented in a good way, and eventually they connected back to the actual injector producer systems in the problem statement. So which is a little different from how other team approached it. But I also want to mention Benjamin Cassidy. He was the single person, and one of the comment about diversity shows there because he brought in some of the biochemistry background and some approaches that he has used in biochemistry, which is a very good sign, I feel like, because you're bringing completely different industries together, and it's adding to adding to the knowledge of overall group, I think. So
excellent. James, what's your take, or what's your favorite team?
I think my take, just to echo everyone else's comments about the diversity, and I think one point to kind of reiterate is how the participants, like who they thought the audience was. So some teams were extremely technically, heavy and dove right into the modeling, and that was, fantastic. If one is kind of a data scientist, others approach it a different way, that they're, reporting to decision makers and people who maybe don't have the technical knowledge. Both were, we didn't put any restriction or any onus on one or the other, but it just goes to show kind of, where people really wanted to personally, push their message across, whether it's the modeling or whether it's, including risk factors in different scenarios. I think my favorite was, I'm a pretty visual person, so I think my favorite was, one individual did a lot of heat mapping and carried that theme through. And you could actually see kind of the spatial distribution of the parameters that he was utilizing. So, I thought that was an excellent way to visualize the problem.
That's excellent. So now we are almost, close to the end. Birol, what do you think? Where are we going from here?
I think in terms of approaches and what we have seen, it would be great to air it in some place and highlight the contributions of all these teams, actually. And it will encourage more participations for the future. And I also agree with all my colleagues. Actually, we had 3 of them I had hard time to distinguish. I would have given awards. We had the same rubric, but I would have given the same different awards for different categories to them, actually.
Yes. So with that being said, we would have liked to have online, voting, but unfortunately that wasn't possible this year. We did have 8 judges, including from DOE, from the Geothermal Technologies Office. And so we are ready to announce the results. And so with that, I think the winners of our Datathon, Pivot Datathon, are the naturals. So the Stanford University team that we are going actually to contact after this and talk with them the details. But this is our work in progress. We are more than happy actually to have this Datathon happening. Thank you again to all the participants. Thank to our committee, to our judges, to our panelists, to Jamie, to the project Inner Space team. Absolutely amazing effort. And we just started. We are going to continue this. You are going to see results in the SPE journals, on the internet, and so on and so forth. But thank you all. And with this, I'm looking forward to seeing more Datathons on geothermal energy. Thanks. Kat.